Honorable Vice Chancellor of Goa University, Professor Devbakar, distinguished invitees, friends, students, ladies and gentlemen. It is indeed a matter of great happiness for me to be able to come to Goa and so this particular opportunity is a matter of double happiness, because on one side I am able to talk to all of you on a subject that is very close to my heart, and secondly I am able to do so in a place which is close to my heart, that is Goa. So I thank Goa University for this wonderful opportunity. What I intend doing in this lecture is to sort of talk about the energy situation, and for doing so I'm going to talk about a time frame which nobody talks. I'm going to talk about a time frame which will be 50 years and beyond. So I'm going to gloss over the time frame of coming years or coming 10 years because I believe that energy issue is much more than just a program implementation. Whatever efforts that are needed, whatever challenges of energy that we need to solve in the immediate time frame, they of course will come about by a good program implementation, and that's the matter of the immediate future time frame. But I think it's also important that we keep our eye on long-term future and prepare ourselves to ensure that we are not caught unawares in light of the tremendous energy requirements that we have and that we are likely to have in years to come on one side, and the tremendous shortages of energy that not only us but the world at large is likely to face. And it is this matter that I want to put it in some perspective before all of you through this lecture. So essentially it has two parts. One, let's say between now and 50 years or 40 years, it will go up to 2050, that is the first part. And then talk about time period beyond 2050. And I believe that by the end of the lecture, you would probably be with me in the rationale for doing so. Can we begin? First one. Now, we have this notion derived from our history that India is a land of plenty. In fact, many of the foreign civilizations came here and in fact ruled here essentially because of that riches that existed, and even now it exists in the country. But then on one side our population is increasing, it is unfortunately still increasing. And secondly, we are going through a rapid economic progress. And both these parameters lead to higher and higher consumption in energy terms, in other materials terms. And so I think time is not far off when it would appear that we have a big crisis about different materials, and certainly energy resource material that is facing us. And this projection essentially makes that clear. Since I'm talking about electricity, I thought we should look at all energy resources in a term which makes a meaning in terms of electricity use or electricity production. So the unit that I have used is gigawatt electric year. Gigawatt is equivalent to 1,000 megawatts or 1,000,000 kilowatts. And so if you generate electricity at 1,000,000 kilowatt level for 1 year, that energy corresponds to a gigawatt electric year. And seen in that unit, all resources, coal, hydrocarbon, uranium, plutonium in fast reactors, thorium, hydro, renewable, solar, they are all listed here in the same unit. How long they will last us? At today's rate of consumption, the number of years they will last us are given in the top row of this table here at the bottom. But the rate of consumption is not going to be stable. In fact, I'll show you later on. Our consumption rate may become order of magnitude higher by the middle of this century. And seen at the rate of consumption consistent with that time frame, the period these energy resources would last is shown in the bottom row. And you would notice that crisis which I am talking about. Coal, which we have in plenty, surely, but at that rate of consumption would last. That is, today's available coal at the rate of consumption consistent with the middle of this century would last for just 11 or 12 years. Hydrocarbon, of course, we use it primarily for transportation sector, very small part for electricity production, but we import most of it. So domestically available hydrocarbon, I cannot even assign a number even at today's consumption because it is so small. Uranium, which is the only naturally available material for energy production, nuclear energy production, even that in once-through mode, or in this case used in pressurized heavy water reactors, at today's rate, if the entire country's electricity were to be produced, it would last just 4 years. And at the higher rate in 2050, it would last a few months. Hydro, even if the entire potential is used, it's not going to be significant. 70, 80 gigawatts is too small compared to something like 1,400 gigawatts, that is the electricity production we expect in 2050. So it looks as if all these energy resources are, in a manner of speaking, insignificant in the context of our future requirements. There are only two sources which will help us in carrying through our business. One is solar and other is thorium. Thanks to the geographic location of our country, something like 4,000 square kilometers of collection area would allow us to collect sufficient energy to meet our requirements at today's rate, and something like 44,000 square kilometers would suffice for meeting our requirements at the rate which we expect in the middle of this century. So, and this is a manageable proposition, provided the solar technology is taken to a level where it becomes commercially viable. Today it is not. Today it has to be supported by several measures, including subsidy, which is of course important. But to be able to make very large scale use, we need to improve technology. So it's a technology challenge, whereas resource is there. Thorium, again, it represents a huge quantity of energy, but you cannot run a reactor on thorium just like that, because thorium doesn't contain any material which can directly fission, because in a fission reactor you have to split an atom, and thorium atom cannot be split just like that. You have to convert thorium into an atom which can be split, and that requires again a technology development, which is embodied in what many of you must have heard, the 3-stage nuclear power development. So you have to begin with uranium reactors. Once you push in uranium in these reactors, some part of uranium gets converted to plutonium, and you use plutonium in fast breeder reactors. In fast breeder reactor, whatever plutonium you consume, you can produce more plutonium. So on one side you produce electricity, other side you produce fissile material. And so you can set up more and more power plants and grow the power generating capacity. And once you do that, then you introduce thorium and convert thorium into another material which can be split, uranium-233. And that's the way you can get the large energy that can be extracted out of thorium. Again, this is a technology challenge. So the point is, while we have done a lot, but we need to capture or gather a capability in terms of these energy technologies, specific, making solar technology commercially viable and getting full technological mastery in terms of utilization of thorium. And it's only on that basis that we can say that we will be able to meet our energy requirements in a time frame of something like 2050, 2060, and so on. Now, fortunately, as far as nuclear energy is concerned, we have this 3-stage program in place, and I'll brief you about the progress to date. So that's well on course. And today we have the solar mission. So I'm sure that will get an impetus, and country will prepare itself for mastering this technology as well. Next one. You have to remember that as you go up to that point of time, or for that matter beyond, we would also remain conscious of the environmental impact of any activity that we do, and energy business is no exception. We have to conduct ourselves in a manner that we maintain, or if we have already degraded, then we in fact restore the quality of air, quality of water, and for that matter, the soil quality. And this is very crucial. This is crucial to our survival. So we must, since we are talking about a very long time frame, we have to keep this factor also at the back of our mind in terms of both meeting our requirements on one side and sustaining the environmental quality on the other. The key to achieving this is, in my view, the number one, we should be able to meet our requirements with the minimum amount of material extracted from earth. And secondly, whatever material we extract and put to use, uh, the, the remainder or the so-called waste, which is not which has not been productive enough, that also should be recycled, because then you maximize, you make more use of the same material. And these two principles, I think, are crucial to any large-scale developmental activity. Do maximum, get a maximum output from a unit material extracted from Mother Earth, and secondly, whatever is left after the one-time use, recycle, so that you get more out of it. And if you do that, then I think we can meet all our requirements. We require air, we require water, we require food, we require material, we require energy to meet the human needs. And there, of course, human needs are of many other kinds, but you can meet them by a combination of these in a manner that you either use it with minimum material, but whatever waste that arises, you recycle and ensure that the earth burden is truly minimum, because I think that's the key to any organization of a large development program. And I want to sort of come back to this theme a little later to tell you how we can do this in a self-consistent manner. Next one. Now let me come back to the three-stage program. In terms of, just for you to appreciate the magnitudes that are possible. See, we have currently a very successful, commercially successful program with a technology which is globally competitive in terms of setting up a pressurized heavy water reactors, and there are several of them which are currently operational, and I'll talk to you, to show you later. What it can do on this large scale, the scale is again in gigawatt electric year. So you can go up to, as we know, 10,000 megawatts with whatever uranium that we have in the country, which is not large, but this is the trigger. This is what will allow you to go to the next stage, as I said earlier. And in fast builder, you can go even higher, but let's say you can go up to 200 or 300 gigawatt electric. Introduce thorium at that point onwards, and then you can go way above 600, 700, 800 gigawatt electric. And this would appear to be a reasonable fraction. This would appear to be something like 50% of the energy, electrical energy that we could be using at that kind of a time frame. So we require a strategy to achieve the required growth profile that can be supported through timely deployment of appropriate reactor technologies, including fast breeder reactor and thorium. And that's what, as I said, the three-stage program is all about, and which is shown in the next projection. In terms of PHWR, I want to emphasize, today it's a indigenous technology developed by the scientists, the engineers in the labs, in the industry, and but all homegrown. And today it operates on a benchmark, on a performance criteria which is comparable or better than the global benchmark, whether in terms of operational characteristics, safety characteristics, in terms of economic characteristics, gestation period, so on and so forth. On every parameter, it is, in fact, this is also reflected by these reactors gaining rewards on the global platform, the World Association of Nuclear Operators. We have several of them, 16 operating, 1 under commissioning, 1 more nearly ready. And then there are 4 more reactors are likely to be set up. The approval has been already granted by the government, and several more units can come in. Another possibility on the first stage is the light water reactors, which use slightly enriched uranium in contrast with natural uranium that we can use in pressurized heavy water reactors. We have the two boiling water reactors at Tarapur operating. In fact, they were the first commercial power reactors built in the country, and they are providing the cheapest non-idle electricity in the country at this moment. There are two more pressurized water reactors under construction at Kudankulam, 1,000 megawatt units each. And now that we have this civil nuclear cooperation a possibility, you expect a fairly large capacity build-up in this category in years to come. And as I said, the uranium used in these reactors will lead to plutonium in the spent fuel, and that plutonium we can use in fast reactors to grow, as you saw in the previous picture. We have realized this technology fully. We've been operating a 40 megawatt fast builder test reactor since 1985, so more than 25 years now. All technology objectives have been realized, and we are actually constructing a commercial prototype, a 500 megawatt prototype fast builder reactor. Again, this is fully indigenous, developed by Indian scientists, Indian industry, and in fact, we are now globally advanced. There are not too many countries who build this kind of power stations, and in fact, when completed, we will be the second country. The PABR would be the reactor, second largest reactor in the world, and that's going to happen maybe a year and a half or 2 years from now. So we are in that situation. So we are moving on the technology development platform. On the thorium front, again, we have on a smaller scale, everything has been done. All aspects of the nuclear fuel cycle and reactor have been tried out. We have a small reactor, Kamini, which is already operating. And a 300 megawatt advanced heavy water reactor is currently under development. And this is what, as we saw earlier, would open up the huge potential, energy potential in thorium in years to come. And we are in fact globally unique. In fact, there is no other country which has such a large interest or technological advancement in this area. Next one. Now, having said that, let us look at the energy situation between now and 2050, because and then we'll see, as I said earlier, the situation beyond 2050. The energy that would require, the electrical energy that we would require, it's a part of a fairly exhaustive, detailed study, but it's projected to follow this curve, the black curve. And I must tell you that this is a study done in DAE, but it's a very conservative study. In fact, the Planning Commission Integrated Energy Policy, which goes up to 2030, those estimates are in fact above this curve. So, although these numbers may look large, please remember that these are fairly conservative estimates. The question is, how do you get that energy to meet this requirement? So what has been done here is that we have looked at all possibilities, all the energy programs in the country, which are being done by different segments in the government, and of course different sectors in the energy business. And this is put there in an optimistic manner. Don't ask questions whether this can be realized or not, because we're trying to look at availability of energy resources. So then optimistic superposition, addition of all programs for different hydroelectric, non-conventional, coal, hydrocarbon, and even 3-stage nuclear power development, which I mentioned to you earlier. If you put all of it together, you come up to this line. and leaving a gap with this deficit remains to be bridged. And the only way you can bridge that deficit now, because you have accounted for all energy resources available in the country, so the only way is to import. You can bridge that deficit only through import. And this is the crucial problem. I'm sure you are aware that even today country is importing certain amount of fuel, coal, oil, gas, even for electricity production, but certainly importing much more for other segments of energy. But this is going to grow, and it will go as high as, in electricity production terms, something like 412 gigawatts, which is roughly 3 times the current electricity production capacity. That much will be the shortage. Seen in the fuel materials terms, if you want to look at it in the form of coal, it will amount to something like 1.6 billion tons of coal annually. And I hope you can appreciate the magnitude of this number. This would choke all our ports, all our railway transportation, quite apart from the question of having to pay for buying these kind of materials, and more importantly, the impact it would have on the prices, because these are large numbers, large enough to affect the world energy prices. So it's a big challenge, but there is no way. You have to import to meet our requirements. And it is in that context that we said that we have come to a good position of our domestic technology development is on a firm path. Our problem is energy resources. So can we import? It doesn't matter whether you import in terms of coal or oil or uranium. So far, import of uranium was not possible. Now it is possible. So supposing we import, can you go to the next one? This is just a scenario, but supposing you import 40 gigawatts of light water reactors in this period, 2012 to 2020, and that is represented by this yellow band. The spent fuel which will arise out of these reactors, you can do the same thing which you are doing on the domestic 3-stage program. You can recycle that plutonium in fast reactors and grow the capacity. And that is shown on this olive segment. And you would notice that by importing fuel, not for 412 gigawatts, as was the necessary in 2050, you import fuel, and that too on a one-time basis initially. For this 40 gigawatts, you can set up rest of the capacity without the need of any additional import. So you would notice that you are reducing your import requirement in cost terms by a factor of 10, which is a very significant factor. And then, of course, you are doing this in a manner where there are no issues related to carbon dioxide. The whole world is now concerned about global warming and things like that. And this is the whole basis on which the international cooperation has been set up. Next one. So as I told you, with following that strategy, it is possible to bridge the deficit and make country energy independent as far as 2050, period up to 2050 is concerned. We can do that on the basis of technology that we already know. The PHWRs, the light water reactors, the fast breeder reactors, and so on. Now, if you have to look at a time domain beyond 2050, we have to be also worried about the global energy scenario. To appreciate that, what is the distribution of energy use worldwide? And you can appreciate that by looking at this map, which is the night picture of the Earth taken from the upper atmosphere, the satellite picture. You can see large amount of domains which are still dark. There is also a difference. You can see very bright patches here. You can also see India somewhat illuminated. But India is illuminated because our population density is very high, although per capita use is low. Other places are illuminated because they use energy at maybe 10, 20 times on per capita basis. So, but the point is, there are aspirations, the buying capability, the economic growth is taking place worldwide. And what's happening in India and China today would also happen in Africa and other parts of Asia and Latin America tomorrow. And all this would mean requirement of more requirement or demand for more energy resources. And a simple back of envelope sum will tell you that so much of resources simply don't exist. And so can we go to the next one? So if you say that a reasonable per capita energy use, we're not talking about 15,000 kilowatt hour per capita or 20,000 kilowatt hour per capita, as is the case in North America or some Scandinavian countries. We talk about 5,000 kilowatt hour per capita as to reach a reasonable human development. Now, even at that level, 5,000 kilowatt hour per capita, considering the progressive depletion of fossil fuel reserves and the urgent need for addressing the global warming related concerns, nuclear energy is expected to substantially contribute to meeting future energy requirements. But what that would mean is, assuming that at least half of the total energy demand may need to be met with nuclear, that's an assumption. But then world would then need between 3,000 to 4,000 nuclear reactors of different capacities. Today worldwide there are around 400 nuclear power plants. So we're talking about 10 times larger number. And this number may at least double if you use nuclear power plants not only for electricity, but also for producing alternate fluid fuel, fossil fluid, alternative to fluid fossil fuel for running the transportation sector. So we're talking about 20 times larger number. And then the question is, where do we locate these reactors? A large number of these reactors may need to be located in regions of high population densities with modest technological infrastructure, with their sizes consistent with local needs. So this is the challenge for future. So although I said that technology, we have mastered this technology, but we will now have, next one, additional demands on this technology. And I'm talking in nuclear. I think same thing will be true in other segments. And the additional demands would certainly be, number one, it should be sustainable. So it should be able to recycle. And that's exactly what we do in fast reactor and even thorium reactors. It should be simple. Nuclear, everybody's fears about this. It's very complex. It can lead to problems. We should make this reactor so simple that everybody feels that, yes, I understand this, nothing can go wrong. It should be super safe, it should be secure. There should be no issue of any problem arising out of malevolent deeds of people. There should be no impact in public domain, and there should be no residual long-term issue. And it so turns out, I'll not go into the more technical details, but it so turns out for all of them, thorium provides an answer. If you want to know what is one single thing which provides the answer, that is thorium. And that's why, according to me, thorium will gain even more importance in years to come compared to what it has been seen so far. Next one. This is the rationale for setting up the advanced heavy water reactor development. This, of course, it will produce a good part of its energy, 2/3 of its energy from thorium. But it has tremendous safety strength. It has a 3-day grace period for operator action. Something goes wrong, even if operator doesn't act for 3 days, in the sense he can call for help, some experts may fly, they may debate, discuss, understand, and put a countermeasure in place. So much of time should be available, no problem. And there should be no radiological impact. Secondly, it should be based on safety systems which are passive in nature, in a manner that they can also address the insider threat scenario. This is very important in the context of the emerging security situation. And then, of course, it should have long life and economic terms and all. Now, this reactor is, as I said, in a very advanced state of development, and I think it's only a matter of little time when one will start seeing construction beginning of such a system. Next one. It's a little technical, but it's just to show that, just like in a car, you have a brake. So assume that you are running car at full speed and the brakes have failed. In this case, the failure of primary and secondary shutdown systems, they have failed. And at the same time, assume, reactor requires cooling. The fuel has to be continuously cooled. Otherwise, it will get overheated and rupture and fission products come out. So assume that there is no power supply, it's complete blackout. And also, in addition to that, at the same time, the shutdown systems fail. Even under that situation, you would notice that the temperature of the fuel cladding, it doesn't rise. And this is what I was trying to say. If you have this characteristic, even if somebody wants to play mischief, he can do no wrong as far as safety is concerned. Next one. Same thing is true about the waste, which is another thing. With thorium, the amount of long-lived radioactivity waste that one produces is way below what happens with plutonium. Next one. I'm almost towards the end of my lecture. But I want to come back to this theme of recycle in the context of both nuclear energy as well as the energy derived from fossil resources. Now, we require energy in the form of what is required for domestic use, industrial use, transportation, electricity. Now, I'm talking about going beyond electricity, heat, and artificial fluid fuels for a variety of other uses. Now, with the continuous increase in demand for energy, and also with continuously increasing threat on the global environment, one thing is you have to go into higher and higher efficiency systems so that you maximize your output for a given energy material that you can derive from Earth. Now, this is true for nuclear, because you get uranium, thorium from Earth. This is also true for the thermal plants which require or which derive coal or oil from Earth. So this is also true for many of the non-conventional energy resources, because after all, if it's a biomass, you derive from Earth. If it is other forms of energy, you derive from sun. So these are the two providers of energy for us which we make use of. In so doing, we produce, of course, wastes. You have produced carbon dioxide, water, other oxides, both light metal and heavy metal, and of course many other products. Now, how do you manage them? we must recycle, because if we don't recycle, then we have to resort to proper waste management strategies. But the better thing is to recycle. Nuclear, we already talked about. We recycle uranium, we recycle thorium to get more fissile material, and it continues. So this cycle does continue. Of course, this continues provided in countries which have adopted such policies. In India, we have adopted this policy right from day one. There are countries which have not adopted this policy. For example, United States. So in their case, you extract nuclear resources from earth, produce electricity, and it becomes a waste. And so they have a Yucca Mountain problem. Now, in case of thermal, again, one can think of a full recycle. The carbon dioxide and water, which is a waste product of this, they are a part of a natural recycle. For example, forget about energy or man-made activity, but the natural activity, we breathe out carbon dioxide, the trees breathe in carbon dioxide and produce oxygen, and so there is an equilibrium. I think same thing can happen in terms of if we use carbon dioxide and water to augment production of biomass. Some will happen naturally, but you could also accelerate that by way of technology, new technology. And then, of course, through biomass, you produce fuel materials, biofuels. But then there is a certain amount of ratio, carbon-hydrogen ratio. Now, if you have your fuel materials, hydrocarbons, in a manner where you have more of hydrogen and less of carbon, you will go towards that much cleaner fuel. Now, how can you do that? While you produce biomass for recirculation, you can also bring in a bit of hydrogen so that the liquid or gaseous biofuels that you produce, number one, they are cleaner, more hydrogen and less of carbon. But at the same time, more importantly, they produce fuels which are exactly equivalent of what is required for running today's equipment. For example, a car running on petrol or diesel. So, because there is a huge investment which exists, so one can, in principle, and I'm not, this actually is a part of a program which I know is currently underway in France. So you can produce hydrogen either directly from sun by way of solar energy, or you can produce hydrogen through nuclear reactors. You can, of course, ultimately, eventually, the hydrogen itself could become a fuel for supporting other activities, transportation and all, but that will require new kind of engines, new kind of equipment. But this is what will happen much later. But in the interim period, we can use that hydrogen, and you can use the carbon and remaining hydrogen from biomass and produce the fluid fuels which are exact substitutes, so that you can run the rest of the transportation system and all the way they are. And if you do so, you would notice you are not adding any extra carbon dioxide into the environment. Whatever carbon dioxide you produce, you bring it back here, and the same thing goes back. So you maintain a carbon balance. And if you can do that, then you reach a very neat situation where you can get as much energy as you want, but without disturbing the CO2 level in the environment. But this again, as I said, is a technology challenge, and I am certain you'll see this happening in some countries in another 5 or 6 years. And I think, given our precarious energy situation, we should find our own solutions for doing so. Next one. So, so we have broadened in the Department of Atomic Energy. the technology R&D has been significantly broadened to include several things, several technology aspects, much beyond the currently known concepts on nuclear reactors. So we're talking about several new things in fast reactor technology, metallic fuel, molten salts. We're talking about liquid heavy metal cooling, high power accelerators, high temperature materials, hydrogen production technologies, of course hydrogen utilization technologies, and fusion. And there are identified deliverables, and you will see this getting realized over a course of time, which will all come in handy in terms of moving towards this direction. Next one. And so the shape of future new nuclear energy technologies, the way I see, are going to be accelerator-driven reactor systems, the high-temperature reactors, hydrogen or liquid fuel production using nuclear energy, solid oxide fuel cells, fusion energy, because everything is finite, so even fission energy will come to an end at some stage. Civilization will go on. So we'll have to go to additional energy sources, so that's fusion. And of course, all important solar energy. And as I said again, but the fundamental thing is, there are only two things which will enable survival of civilization. One is solar, and the other is nuclear. All other energy sources are of course important, and we must make full use. But seen on the scale of use consistent with, let's say, turn of this century, they will all appear very small. And these are the only two things which you have to work on. Nuclear energy, which is fission and fusion, and solar energy. Thank you very much.